Picture a single plastic gallon jug of diesel fuel.
Okay, like a standard milk jug.
Yeah, exactly. Now imagine using just that 1 gallon to move an entire ton of freight over 436 miles.
It sounds physically impossible, honestly.
Right, especially when you compare that fuel economy to, your daily commute. But welcome to today's deep dive. We are unpacking Module 6, Section C of the APCS, Certified in Logistics, Transportation, and Distribution, or CLTD learning system.
And our mission today is to really get into the weeds of rail transportation characteristics.
Because it is definitely not some outdated relic of the 19th century.
Oh, far from it. It's an absolute powerhouse. We're going to explore how its totally unique infrastructure impacts the modern global supply chain.
And exactly how you can leverage that massive capacity and those cost efficiencies.
Because that staggering level of efficiency comes with a very specific set of rules. I mean, we like to categorize transportation neatly, but the rail industry is incredibly complex.
Mostly because it is entirely bound to the ground it sits on.
Exactly. The literal groundwork.
Right. So before we can really understand how trains move our modern goods, we have to look at that infrastructure. Because it dictates everything about this mode's capabilities and its limitations.
It really does. If we trace the history just briefly, rail was the absolute driver of economic expansion in the 19th century.
Like the U.S. Transcontinental Railroad opening up the West.
Right. But then it waned significantly, like right up through the 1980s as the highway systems grew and trucking basically just took over everything.
Yeah, in the 80s, rail was widely considered pretty archaic. Supply chains were speeding up, and people thought railroads simply couldn't meet the, agile needs of modern freight.
But then it made a massive comeback in the 1990s.
And the primary catalyst for that renaissance was containerization, right?
Yes, standardized steel shipping containers. They changed everything.
Because suddenly, rail wasn't just this isolated, standalone network. It could integrate seamlessly with ocean and road transport.
Right, without workers having to manually unload every single box from a train to a truck.
Which is huge. But looking at these infrastructure costs in the U.S. in our sources, it frankly seems like a terrible business model compared to trucking.
It is definitely a completely different beast.
Because the way infrastructure is owned completely changes the game depending on where you are in the world. In the U.S., private railroads actually own the tracks.
They own the tracks, the terminals, the rail yards, the equipment, all of it.
Why would anyone take on that massive capital burden? To put that U.S. model in perspective for you, it's like a trucking company trying to operate, but
instead of using public highways.
Right, public highways paid for by taxpayers.
Mm-hmm.
Instead, they have to literally buy the land, pour the concrete, and build their own private interstate just to drive their trucks to work.
It's a great analogy. The barrier to entry is just astronomically high.
I mean, no one is starting a new Class I railroad tomorrow in their garage.
Exactly. But the payoff is total control and near monopoly pricing power in certain regions. They bear the entire capital cost, but they don't have to share their private interstate with anyone else's trucks.
Which is totally different from the European Union.
Right. In the EU, electric-powered rail infrastructure is heavily subsidized by governments to promote green transit.
And in most other places around the world, rail infrastructure is simply state-owned and maintained.
Operating much more like the public highways in your trucking analogy.
Which totally explains why global rail networks look the way they do based on, who is actually funding them. Our sources break them down into a few main categories.
Yeah, first you have penetration lines.
Which you see a lot in developing nations or resource-rich countries like Canada and Australia.
Right. These lines basically exist primarily to link port cities to the interior, just simply to extract natural resources.
Then you have regional networks.
Mm-hmm.
These serve high-density populations like in Western Europe, Japan, and coastal China.
And finally, transcontinental lines, which act as massive land bridges across North and South America.
Speaking of massive land bridges, we have to talk about China's Belt and Road Initiative, the BRI.
Oh, absolutely. They are pouring over $1 trillion into this global infrastructure network.
And a huge part of that strategy is using rail to bridge the gap between really expensive air freight and very slow ocean freight.
They're attempting to literally reshape global supply chains by developing the middle corridor.
Right, which runs from China to the EU and terminates at the Caspian Sea.
Geographically, it looks incredibly smart.
I mean, it's the most direct route on a map. It saves about 2,500 kilometers in travel distance compared to other overland options.
But the reality of the supply chain doesn't always match the ambition of a map.
Yeah, because according to our sources, the lead times on that middle corridor can still be 50 to 60 days.
Which sounds crazy.
It does. Why is it taking 2 months to move a train across what is technically a direct route?
That delay perfectly illustrates a fundamental logistics problem, which is the friction of transshipment.
Tell me more about that.
Well, when that train hits the Caspian Sea, it can't just, drive onto a boat.
Obviously not.
Right, so the containers have to be lifted by these massive gantry cranes onto a maritime vessel, then sailed across the sea, lifted off by another crane on the other side, and placed onto an entirely different rail system.
That is so many touch points.
Exactly. You are at the mercy of port congestion, weather variables, and scheduling misalignments at every single one of those touch points.
Plus, the sources point out severe capacity limits on those routes. Like, for instance, trains heading from Beijing to Tehran max out at about 220-foot equivalent units, or TEUs.
And for context, some North American trains can haul 800 TEUs at a time.
So you essentially have this massive bottleneck where huge volumes of freight are being squeezed through a really narrow multi-step transshipment funnel.
Yeah, and that massive difference in throughput connects directly to how different regions solve their economic equations.
Because of that massive capital investment in infrastructure we just talked about, railroads have to be incredibly strategic.
Highly strategic about the specific types of freight they target and the operational strategies they use just to make a profit.
So let's look at that operational setup. The industry categorizes carriers by distance, primarily.
Right. You have line haul carriers, which are traveling over 350 miles.
And regional carriers covering about 400 to 650 miles.
And short line carriers, which operate on under 50 miles of track.
And those short lines are often used for local drayage, right?
Exactly. Basically moving cargo short distances from a major rail hub to a final manufacturing plant, or maybe a port.
But the hardware they use on those tracks is what's really fascinating. It's obsessively specialized.
It is. The basic unit of measure is the carload. And the standard vehicle most people picture is just the boxcar.
The classic train car.
Right. But it gets much more specific than just a rolling metal box. You have hopper cars, for instance.
And those carry loose bulk commodities, right? Like coal, grain, or sand.
Yeah. And the key feature of a hopper is that it uses gravity to unload. The bottom literally opens up and the freight just pours out between the tracks.
Oh, wow. Okay, so what about gondola cars? Because they also hold loose materials, right?
They do, but a gondola is essentially just an open-top tub. It doesn't have that gravity release bottom of a hopper.
So how do you get the stuff out?
Well, if you're hauling heavy scrap metal or, huge steel coils, you load and unload a gondola from the top using a crane or a giant industrial magnet.
Okay, that makes sense. Then you also have flat cars for large vehicles or containers, tank cars specifically pressurized for liquids and gases.
And reefers, which are refrigerated cars. Those are absolutely essential for the agricultural cold chain.
And when you look at the actual commodities moving in those specialized cars, the volumes are almost impossible to comprehend.
Staggering numbers.
Truly. In a single recent year in the U.S., rail hauled 1.5 million carloads of grain, 3.4 million carloads of coal, and 2 million carloads of lumber and paper.
And to put 3.4 million carloads of coal into perspective.
Please do, because it's hard to visualize.
If you lined those standard 50-foot rail cars up bumper to bumper, they would stretch over 32,000 miles.
That's insane.
That train would wrap entirely around the Earth at the equator, and you'd still have enough cars left over to stretch from New York all the way to London.
Okay, that visual perfectly captures why rail is the undisputed king of heavy, bulk, weather-impervious commodities moving over long distances.
Yeah, no other land-based mode can even touch that capacity.
But those massive numbers rely on a very specific operational choice, which our sources highlight: the difference between unit trains and manifest trains.
This is a crucial distinction.
Because if I'm shipping coal, I'm not just, attaching my single car to a random train heading west.
Far from it. This is where railroads find their peak efficiency. A unit train is a massive train, sometimes up to 2.5 miles long, carrying a single commodity.
Often just for a single customer, right?
Exactly. It might be entirely coal or entirely grain. And because every single car is going to the exact same destination, a unit train completely bypasses the rail yards.
It just runs nonstop from the origin point to the destination.
Right. Whereas a manifest train is a mix of everything.
It's the train you get stuck behind at a railroad crossing, where you see lumber, then a tank of chemicals, then a boxcar of auto parts.
Yeah, and because a manifest train is carrying mixed freight for dozens of different customers, it has to stop at classification yards along its route.
And what happens there?
Well, at these yards, the train is essentially uncoupled, sorted, and completely rebuilt.
Which sounds time-consuming.
Very. Cars are pushed over a literal hill. It's called a hump yard, so they can roll down using gravity onto different branching tracks.
To be attached to new trains going in specific direction.
Exactly.
Yeah.
But that classification process takes days, and it adds massive lead time to the supply chain.
I can definitely see how that slows things down. But as a learner diving into this, if I'm managing a supply chain for an electronics brand or an apparel company, and I definitely don't ship 3 million carloads of coal, why should I care about rail?
That is the big question, and the answer lies in multimodal innovations. Rail doesn't just move coal, it moves the everyday consumer goods you buy online.
And it does so by integrating seamlessly with the trucks that eventually deliver to your local warehouse.
Yes, through something called TOFC, which stands for Trailer on a Flat Car, often called piggybacking.
You literally take a standard highway truck trailer, detach it from the truck cab, and use a crane to lift it directly onto a rail flat car.
Exactly. And even more impactful is COFC, Container on a Flat Car. This is where you see double stacking.
Stacking 2 shipping containers on a specially designed flat car that sits very low to the ground.
This specific innovation fundamentally changed global trade.
Right, because a container can be packed at a factory in Asia, loaded onto an ocean vessel, craned onto a double-stack rail car in Los Angeles, moved all the way to Chicago, and then dropped onto a truck chassis for final delivery.
And the freight itself inside the box is never touched by human hands during any of those transitions.
That's brilliant. So let's talk about the business side of this, because once you combine this privately owned infrastructure with highly specialized high-capacity equipment, you get a really unique economic and environmental profile.
You really do. In the U.S., because of the massive capital required to lay track, the market is a pure oligopoly.
Yeah. 7 Class I railroads, those are the ones with revenues over $448 million. They command 94% of the rail freight revenue.
And this consolidation creates a very specific economic dynamic known as captive shippers.
What does that mean in practice?
Well, if a company builds a massive manufacturing plant or a chemical refinery, and it is geographically only serviced by one single rail line, they have zero alternatives.
They cannot call a competitor because the competitor's tracks literally do not go to their facility.
Right. They are entirely captive to the pricing of that single railroad.
They can't just switch vendors like they could with a trucking carrier.
No, which is why there's a constant ongoing push for rate relief and regulatory oversight in the rail industry just to protect those shippers from price gouging.
And the railroads justify their rates by pointing to their cost structure, which is completely inverted compared to trucking.
Yeah, railroads have incredibly high fixed costs. Buying the land, laying the steel tracks, building the terminals, purchasing multi-million-dollar locomotives.
But once those fixed costs are paid, their variable costs, like the cost to actually move the next ton of freight, are incredibly low.
Very low.
What I found genuinely surprising in the sources is that labor is actually their largest variable cost. Train crews, maintenance workers, terminal staff, they account for about 1/3 of operating expenses.
Fuel is only the second largest variable cost.
And that low fuel cost brings us right back to that opening thought about the single gallon of diesel.
Exactly. A single rail car can carry the freight of more than 4 full semi-trucks.
So when you scale that up, rail is 3.5 times more energy efficient than trucks.
The environmental numbers are honestly super compelling. In the United States, rail accounts for only 1.7% of transport greenhouse gases.
Compare that to trucks, which account for a massive 23%.
And in the EU, where we mentioned most of the network is electrified, rail emits less than 1.5% of transport CO2.
And the industry is actively pushing that advantage even further, right?
Oh, yeah. In the U.S., there's a major regulatory shift toward Tier 4 locomotives.
And this isn't just like a minor software tweak for better gas mileage.
No, it requires massive physical changes to the locomotive's engine and exhaust systems. It essentially acts as a mobile chemical treatment plant, scrubbing the exhaust to reduce particulate emissions by 90% and nitrogen oxide by 80% before it ever hits the air.
Okay, so wait, let me play devil's advocate here. If rail is incredibly cheap for long distances, handles massive volume, and is drastically better for the environment, why isn't every single thing shipped by train? Why do trucks dominate the highways at all?
Right. That is the ultimate reality check for this mode of transport. The answer comes down to friction and absolute rigidity.
The exact same fixed steel infrastructure that makes trains so incredibly efficient is also what severely limits their flexibility.
You can't just swerve a train around a traffic jam or detour through a different neighborhood.
No, you definitely cannot.
So let's start with the most fundamental physical limitation, the rail gauge.
Gauge is the width between the two steel rails on the ground.
Right. Standard gauge is 4 feet 8.5 inches.
Which seems like a weirdly specific number until you realize it historically traces all the way back to the axle width of Roman chariots and early British coal wagons.
It's a very old standard. But the crazy part is standard gauge is only used by about 60% of the world's railroads.
The remaining 40% use broad gauge or narrow gauge.
Which is, it's a huge problem.
It's exactly like traveling internationally with your electronics and realizing you have the wrong wall adapter.
Yes.
Or trying to plug a brand new USB-C cable into an old USB-A port. You have the power, you have the device, but the infrastructure simply doesn't match up.
That is the perfect analogy. Now scale that frustration up to a supply chain moving millions of dollars of inventory. It's like having to download all your data onto a physical hard drive, walk it over to a new computer, and re-upload it just because the cable didn't fit.
Wow, yeah. And globally, this interconnectivity problem is severe. Countries like India, Bangladesh, Australia, and Brazil have different gauges either right at their international borders or, incredibly, within their own borders.
And when a train hits a gauge change, everything stops. You have to undergo that transshipment process we talked about at the Caspian Sea.
You literally have to lift the cargo off one train and place it onto another train built for the wider or narrower gauge.
Right. It requires heavy machinery, it is extremely costly, and it brings the supply chain to a grinding halt.
And the physical environment creates other barriers too, beyond just the width of the tracks. Like in Europe, they desperately want to utilize double-stacking containers, that COFC innovation we discussed.
Right, but they really struggle to implement it because their network is highly electrified. They have electric power lines hanging right over the tracks.
They literally do not have the vertical clearance to stack two shipping containers on top of each other without hitting the wires.
Exactly. Then there's the issue of schedule flexibility. Trains can't reroute around an avalanche in the mountains or a new housing development in a city.
And in many urban areas, freight trains have to share the tracks with passenger trains.
And passenger trains almost always have priority. If a commuter train is running late, the freight train is ordered to pull over onto a sidetrack and just wait.
So a freight train's timetable is fixed, it's slow, and often it just does not align with the agile, on-demand requirements of modern e-commerce businesses.
Not at all. There's also the physical reality of the ride itself.
Yeah, we tend to think of a train gliding smoothly on continuous welded steel rails, which is mostly true when it's cruising at speed on the main line.
But cargo safety during the yard sorting process is a massive concern.
While generally safer than road transport from a collision standpoint, cargo on trains is subjected to severe physical shock during a process called shunting.
This happens in those classification yards we mentioned where manifest trains are assembled.
Anyone who has lived near a rail yard knows that sound, that huge, echoing, metallic boom when the cars connect.
That boom is pure kinetic energy. When a 100-ton rail car rolls down a hump yard and slams into a stationary car to couple with it, even at just 4 miles per hour, the force transfer is immense.
It sends a shockwave through the entire structure.
Exactly. And because of this severe vibration and longitudinal shock, shippers have to invest heavily in specialized dunnage, blocking, and bracing inside the containers.
Yeah, if you don't secure your pallet of electronics or machinery perfectly, that shunting impact will destroy the goods before they even leave the yard.
That's a real risk.
So, wrapping all of this up, the key takeaways from our sources paint a very clear picture. Rail transportation is an absolute powerhouse of the global supply chain.
It offers unmatched volume capacity, it is incredibly cost-efficient for long overland distances, and its environmental footprint is vastly superior to trucking.
However, to actually use rail effectively, supply chain managers must respect its limitations. You must have the luxury of longer lead times to absorb those yard delays.
You have to be prepared to work around rigid, unyielding schedules.
And you absolutely must utilize strong multimodal planning to navigate its geographical and infrastructure boundaries.
It takes real strategy.
Which leaves us with a final thought to ponder as you look at your own logistics strategies. We're watching global corporations face intense, unprecedented pressure to radically reduce their carbon footprints, right?
Oh, massive pressure.
But at the exact same time, consumer demand for next-day e-commerce delivery has literally never been higher. So, will the desperate need for green logistics spark a massive renaissance in rail transport? One that finally forces neighboring countries to standardize their rail gauges and rebuild their infrastructure.
Or will the relentless demand for speed keep rail forever relegated to just moving our coal, our grain, and our heavy containers in the background?
It's a tension that will absolutely define the future of the supply chain.
It really is the ultimate trade-off between sustainability and speed, and how we solve it will change the map of global trade.
Well said. Thank you for joining us on this deep dive into the APC CLTD learning system. We hope this helps you keep exploring the why behind the supply chain.
And the next time you see a train rolling by, just remember that crazy statistic.
436 miles, 1 ton of freight, and just 1 single gallon of fuel. Until next time.